Okay, so this is going to be calculations with strong acids, weak acids, strong bases, weak bases. So I think I have a lot of questions here. I might walk through a couple of them and then I might pause and let you try some of these on your own as best as you see fit. Okay, so just a reminder for what weak acid equilibrium. This isn't for strong acids, this is for weak acids. For strong acids, we assume that the equilibrium is so far to the right that we don't really worry about it. It's not really an equilibrium at all. But for weak acids, this is usually the form that we tend to use. It's a little more simplified. This is more of actually what's going on, but if we use this form, this will reduce down to this right here, where this is a generic anion of the acid, and the proton, and this is the generic weak acid. Now, HA isn't always necessarily neutral to use this. This isn't always a -1 charge. What this is symbolizing, here as well, is that whatever this is always one more negative charge than whatever that one is. Okay, similarly for weak bases, this is not for strong bases, this is for weak bases only. You get this, and if we're making the equilibrium, water's a liquid, so it doesn't appear down here, so products over reactants, here's your equilibrium. And same deal, this isn't always a +1 charge protonated base. The normal base isn't always neutral. Whatever this base is, this will have one more positive charge than that. That's all that really means. Okay, so first off, the strong acid calculations. Determine the pH of 2 molar sulfuric acid. So I'll try that the best I can. Maybe I'll need a little bit more room, but we'll try it. All right, so this is going to break apart into well, I'll just write it down. What this pretty much does on its own is it breaks into this and that right away. Okay. After that, there's an equilibrium on what this is called the bisulfate ion. So anyway, 2 molar sulfuric acid is exactly the same as saying 2.0 molar hydrogen ion concentration. So what I do for this is I use pH equals the negative log of the hydrogen ion concentration. pH is going to equal negative log, and when I'm saying log, I mean base 10 here, of 2.0. And let's just see what I end up getting. I'll switch to my EduCalc here. Negative function log base 10 of 2. And I'll hit enter. And, I gotta get myself out of the way. It looks like my pH is negative 0.3 molar for this one. Negative 0.3 molar, sorry. Negative 0.3. And that's that. And that should be about as straightforward of a calculation as you're going to get in the questions to come. So now here is one that takes a little bit of a roundabout way. What I would recommend you do is you pause the video now, try to solve this. When you come back and unpause, I am going to have my calculations sitting there already done. I'm not going to. I might walk through them once they're already written down, but yeah, that's what I'm going to do. So pause right now. Okay, here are what my calculations are going to look like. All right, here's my answer for this. So because this is a strong acid, 1.5 molar nitric acid is equal to 1.5 molar proton concentration. If I take the negative log of the H plus here, I get a pH of negative 0.18. Now at this point, to get hydroxide concentration, I can figure out the POH using, pH plus POH equals 14, and then do 10 to the negative POH power. That's one way. I chose to use this method. The kW of water, the equilibrium constant for the dissociation of water, is 1 times 10 to the minus 14th. And I already know what H plus is. I know it's 1.5. So I just plug it in here in this equation right there. And then I divide this by 1.5. And then I get the concentration of hydroxide, which is 6.67 times 10 to the minus 15th molar. So yes, even in a strong acid, there are a very small amount of hydroxide ions sitting in there. Okay, so now what about a strong base? So one thing I'll just kind of use to get you started on this is that if, same thing like with the acid, when you have a strong base, this is going to completely dissociate into potassium ions and hydroxide ions. 1 to 1, right? So every time If I've got 0.2 molar potassium hydroxide, really, what do I have? I also have hydroxide ion equals 0.2 molar. So starting from that, why don't you pause right now and see if you can calculate this out. I can think of two ways, so I might actually run through it two different methods here. Split the screen maybe in half. And then when you unpause, I'll have my calculations all set for you. So go ahead and pause now. All right, so you can see I did it two ways here. And one way, I like the blue way a little better. I don't know why. Maybe it's because I don't have to deal with scientific notation. But it really doesn't matter, whatever works for you. And so I figured out first the pOH. If you do the negative log base 10 of OH, you get the pOH. So negative log base 10 of 0.2, and that gave me 0.7 for a pOH value. Then I used the formula that, pOH plus pH equals 14. Plugged in 0.7 here for pOH, and I can just do subtraction and solve, and I get that the pH is 13.3. Now on the other side there, I could also use the dissociation constant of water, which is if you multiply the hydroxide and the proton concentration, you get 1 times 10 to the minus 14th. I already know that OH is 0.2 from over here, so I plug it in, and I divide both sides by 0.2 and solve, and I get the proton concentration. So pH now can be found from this. It's the negative log of that, so there it is, and I still get 13.3. All right, let's see what's next. Okay, now things are going to get a little bit more interesting for solving, because now we're moving to weak acids. So 1 molar HF is not the same thing as 1 molar H+. If it was, this would be very simple. I'd do negative log base 10 of 1 and I'd be done. Unfortunately, weak acids take a little bit more than that. So here's what we have to do. We have to set up the acid equilibrium. So Ka equals H plus times F minus all over, in this case it's HF. And think about what this is going to look like. Okay, so where did that come from? That came from this equilibrium right here. And everything's aqueous. I didn't put the AQs down. A minus. I'm sorry, instead of A minus, I'll just write out what it actually should be, F minus here. But sometimes people would use A minus generically. So that's where I got that Ka expression from. And if we're going to start, if we did like a rice table here, we got R. Initially, we're going to have 1 molar this and 0, 0. And then all of a sudden it breaks apart. The change is negative X, X, and X. So at equilibrium, HF is 1 minus X, X, and X. So that's where this was going to come from. You're going to see this repeated probably a lot of times, so it's just going to start to become second nature to you. If, like I did with the equilibrium stuff, I take this and I place it in here, and keep in mind, I do know what Ka is. It's given to me. So I'll place those things into that expression. I'm going to get 7.2 times 10 to the minus 4th equals X for H, X for F minus, and 1 minus X for HF. All right, so now we could solve that directly for X if we wanted to. But you know what? Since I see that my Ka value is fairly low, this is going to mainly stay, it's a weak acid. It's going to mainly stay as HF. It's not going to dissociate into H plus and F minus very much. So this 1 minus X is approximately equal to 1. So this is going to be, I'm going to make that assumption like we did with equilibrium. 10 to the minus 4th is approximately equal to X squared over 1. It makes the solving a little more simpler, like, okay, so now all I need to do is take the square root of this value. So I'm going to pause real quick and do that. All right, so if you take a look here, I've done the square root of this value, and I solve for X. X is just H plus. So now I know the H plus concentration, and then this becomes somewhat easier at this point once you are right here. Okay, so now if I want the pH, I'm going to do the negative log base 10 of H plus, which in this case is 0.0268, which is going to equal, let me pause and do that real quick. All right, I get an answer of 1.57. So we have to use the equilibrium calcs first to figure out what H plus is for a weak acid. Okay, so here's one that is very similar. I would say pause the video right now, and then I will show you what my calculations are in just a second. So go ahead and pause. So you maybe notice my background changed a little bit here, and I had to finish this video up at a later time of the day in a different location. So here you go. Here's the answer to number 5. Is this what you got? Did you get something like this? Well, then congratulations, partly because you must have understood question number 4. And you went through and you broke things down in the correct equilibrium there, and you put it in there and you made that great assumption, wonderful assumption, that 0.01 minus x is approximately just 0.01. And you went through and solved, and this is what you got. Unfortunately, you made a mistake. So if you got this, I would say the good news is at least you understood kind of how number 4 worked. The one thing that you made a mistake of is that acid constant, -2 order, that's not terribly small. And let's also look at the assumption we made. We made that assumption that 0.01 minus x is approximately just equal to 0.01. Well, look what x is. And if you plug that in for x, you're going to get like a negative value here. That's certainly not something that we can do. So what I'm going to do is tell you to pause again if you've done this, erase what you've done, and solve up for x a proper way. And then I'm going to erase my stuff here, and we'll see what the actual answer, the true answer should be. Okay, so the difference here is that I didn't feel like doing a quadratic. You could definitely work this out, get a quadratic equation and solve. I felt like using a solver, which randomly, on my calculator, which just randomly throws in values till it finds the one it likes. And I get x is this value. X is the same as h plus, so I can take the negative log of h plus. I should maybe write that in there, that this is equal to h plus. And therefore, I get a pH equal to 2.19. So with this next question here for number 6, I'm just going to kind of take a look at how I might go about setting this up. And something like HOCl is in equilibrium with H plus and OCl minus, and maybe I'm starting initially with 0.5 molar of this stuff, and it's going to break down 0.5 minus x, and x. So that's what it would look like at equilibrium, and I could plug in those values here. Ka equals x for H plus, x for A minus, in that case that's OCl, is A minus, and HA would be HOCl, 0.5 minus x. And I could, you could try to make the assumption about the 0.5 minus x, but I don't know why you would, because we're going to know what x is here in a second. If I know that the pH equals 3.88, we have a formula that says 10 to the negative pH power equals H plus, which in our case is the same as x for this. So let me just pause here real quick and do 10 to the negative 3.88 power. Okay, so at that point, I get x, which is the same as the H plus concentration, is 1.32 times 10 to the minus 8. So I plug that in for x in all 3 spots, and I get 1.32 times 10 to the minus 8 squared on top, because I'm just multiplying it by itself. And I actually plugged it in for x. Now, we know here that I could make the assumption that this is probably about 0.5. You can keep using it. If you on your calculator, you can easily subtract this from it. I don't think it's really going to make the difference too much. But that's exactly what Ka is going to be. Let me just type it in and get you a number real quick. Okay, so I get a value of Ka equals 3.48 times 10 to the minus 8. Okay, so on this one, I will let you answer it. And I'm going to pause my recording and I'll give you the answer. So go ahead and try to answer it. Pause the video, see if you can get it right. Okay, here's your answer. 2 parts. First OH minus. I decided to go figure out what the POH was first by doing pH plus POH equals 14, and then figuring out POH from that. Lastly, doing hydroxide ion equals 10 to the negative POH power, and that's my answer right there for hydroxide. Separately, I figured out what does H plus equal, 10 to the negative pH power, and this is what H plus is. If I write apart the equilibrium expression, well, x is the same as H plus. Here's what Ka would be. It'd be x times x divided by 0.1 minus x. I plugged in x here, and here it would be, oops, didn't mean to do that, sorry. Here's my value for Ka. Okay, now jumping over to how do you do stuff with weak bases. So here I've got a weak base, aniline, which is going to be, let's just call it B. And recall that bases, they react with water liquid, and they become protonated. And then they'll make hydroxide ions. So what does this look like? This would be the C6H5NH2 would be B, and BH plus would look like C6H5NH and have a third H, so NH3, and there'd be a plus charge on there. So I need to go ahead and try to figure this one out. Oops, looks like I'm in the way a little bit again. There we go. So that's what this would end up being. We need the pH of a 2 molar solution of this base. So let's go ahead and try this. Initially, the base is going to be at 2 molar. And water we don't care about. There's no molarity initially of those things. Well, what's going to happen at equilibrium? The base will be 2 minus X, some sort of concentration. And then we'll have X of our protonated base and of our hydroxide ion. So now we can actually go ahead and solve for X. Kb, which is very, very small, 3.8 times 10 to the negative 10th, is going to equal this here, this protonated base, which is X, times the hydroxide, which is X. So I'm going to get an X squared on top. And I'm going to be divided by the reactants, which water liquid doesn't show up inside the equilibrium expression, but 2 minus X does for the base. So that's going to go on the bottom. And I could go ahead and solve for X here if I'd like, but because that this equilibrium constant here is so small, or so much smaller than 1, it's in the order of 10 to the minus 10th, I can assume that this, this on the bottom here is approximately equal to 2. 2 minus X will be about 2. That aniline concentration is going to roughly stay 2 at equilibrium. So this is approximately equal to X squared over 2. All right, I'm going to pause and solve for X here. Okay, so doing that, I solve for X, and I get, X is also the hydroxide concentration. I get 2.76 times 10 to the minus 5th molar hydroxide. But the question's really asking what is the pH. So I have to take these a little bit further. Weak acid ones, they seem like they can maybe go a little bit quicker than these ones, but that's okay. You just have to do some other steps. I like going the pOH route. So I'm going to do the negative log base 10 of that OH concentration, 2.76 times 10 to the minus 5th, because that's going to give me my pOH value. So I'll do that on my calculator right now as I speak. And I'm getting a pOH of about 4.56. So now the last thing that I would like to do is use the idea that pH plus pOH always equals 14. So if I plug in, pH plus 4.56 equals 14, I can figure out what my pH is, and I get pH of this equals 9.44. There's my answer. So that's how you do weak base. It seems like you got just a little bit of a roundabout question where you probably would have had pH here in a weak acid type question. You have this little extra step here. I like to go the pOH route. It just seems like it works better for me. But what you could have done is you could have done this equal, this times proton concentration equals 10 to the minus 14th. And then you can divide and get H plus. And then you can do negative log of the H plus. And it doesn't really matter. It's going to get you to the same sort of stuff. All right, here we go. We got another weak base here. This is similar to like an ammonia type thing. NH3 is ammonia, so you got NH2, and then instead of one of the H's, we tack on this C2H5 group on the end. It is a weak base, and I'll let you go through and see if you can't figure out what the Kb value is. I'm going to pause the video. Why don't you pause, work out the question, and then you can go ahead and see my answer when you unpause. All right, so here's how I did the question. I first started with pH, and I wanted to figure out what pOH was first, right? So I use this relationship that if you add pH and pOH, it has to always equal 14. So I plug in pH here, I can solve for pOH and get 1.48. Then I use that and said, okay, 10 to the negative pOH power gives me hydroxide. So here's my molarity of hydroxide. And I kind of saved that, and separately, I wrote out the equilibrium here for what base does here. When it reacts with liquid water, it gets protonated, it steals a proton from water, and it makes the protonated base plus hydroxide. So initially we started with 2 molar of the base, nothing of the other 2 species. And then at equilibrium, we're going to lose some of this, so 2 minus X. And then we're going to gain X of both of those. Well, I know what hydroxide's concentration is, so that is X right there. All right, so if I set up the equilibrium, it's going to be products over reactants. So there it is. Water doesn't appear down here because it's a liquid. So really, what is this? This is X. Here's X. And then we got 2 minus X for that one. But I know what X is, so I can plug that number in for X and just go ahead and solve for KB. And there is my answer for KB. Okay, last question here. It looks like this one maybe I cut off a little bit on the slide thing, so I do apologize, but it still works. How many grams of the CH3NH2 must be dissolved in 1.5 liters of water to give a pH equal to 10? Here is the KB of this base. Okay, this is a tough one, so I'm going to let you go ahead and try to solve this. Pause the video, and then when you unpause, you should see my calculations again worked out, and I will run through them. So good luck on this one. All right, so here we go. So I didn't even fit the whole question on this one screen here, but let's first do this. I start off, I want my pH to be 10. So I did pH plus POH equals 14. I can get POH equals 4. That means I need a hydroxide concentration, molarity of 10 to the minus 4th. Separately, I have the equilibrium here, and I don't know what this starting molarity is. If I could do that, that would actually really help me solve this question, but I don't know what that is, so it's some question mark. I'm going to start initially at 0 and 0 here, and that question mark, whatever I start with, I'm going to lose some of it, so minus X, and I get X of each of those. And just like last time, we know what X is. It's 10 to the minus 4th. So now I'll plug that in for what is KB. KB, 4.4 times 10 to the minus 4th, there it is, equals X squared, X times X, over that question mark minus X. I just kind of changed the question mark now to CH3NH2, original concentration. I know what X is. It's 10 to the minus 4th, so I just plugged it in for everything. And then I solved for what is CH3NH2. This is actually not that hard to solve for. If I multiply this whole denominator by this, I can then take 1.1 times 10 to the minus 8th divided by that number, and then I'll just add on 10 to the minus 4th to that, and this is the answer I get. So this has to be the original molarity of that base. Now the question is, well, if that's the original molarity that I want to have, and I'm going to use 1.5 liters of water, how many grams of that base am I going to need? So that's where the next part comes in. So there's that. I just copy that molarity down. Molarity is moles per liter, but I want that many moles in 1.5 liters, so I multiply it by 1.5 and find out I want that many moles. Maybe I'll just put that in there of the CH3NH2. Okay, so then that's how many moles of the CH3NH2. Maybe I should have added that in there. And this is the molar mass right here. Molar mass of CH3NH2. And that every mole of it that I have is 31.07 grams. Multiply that, and there you go. That's a real small grams amount. It's like a little over 5, almost 6 milligrams, it looks like. In 1.5 liters of water, and we should get that pH of 10. So that's a pretty tough, involved question, but there you go. It's done, and hopefully you got close to the answer, if not got the answer.